Thanks so much for that introduction, and I'm really excited to be here today to tell you all about some of the work that I've been doing over the course of my PhD to develop transition metal oxides, oxide alloys of TiO2 and various other materials for solar-driven water oxidation. So Madhur sort of already gave a nice intro to photoelectrochemical cells, but I'll sort of give my pitch as well. So the overall goal of my research is to be able to convert solar energy into a chemical fuel. And one way that we can do this is through a photoelectrochemical cell. And this picture is probably familiar to a lot of people in the audience, but if not, all this is we're taking two electrode materials, immersing them in solution. Those materials absorb energy from the sun, and then they use that energy to drive chemical reactions at their surface. And so we typically break up one of these photoelectrochemical cells into two components. We have the photoanode, which is on the left, where we oxidize water to form oxygen gas, protons, and electrons. We then shuttle those protons and electrons over to the photocathode, where they recombine to form hydrogen gas. And so the net reaction here is taking water and splitting it to form oxygen and hydrogen. And in this case, the chemical fuel that we're forming is hydrogen gas. But what I actually think the more important take-home message from this slide is that no matter what chemical fuel you want to make, it doesn't necessarily have to be hydrogen, you need a source of electrons. And the most obvious choice for generating those electrons at a large scale is from the oxidation of water. And so my project has really focused on that photoanode side and trying to develop materials that are both efficient and stable for that process. So if we zoom in on the photoanode and look at what that's actually made up of, the structure that I work with is called a metal insulator semiconductor junction. And this allows us to interface high-quality semiconductors with very efficient catalysts. And so the structure is shown here. We have our base semiconductor. We're using silicon in this case. That's the material that's absorbing the energy from the sun. We have SiO2 as our insulator. It's very thin, just 1 or 2 nanometers. And then finally, we have the metal contact on top. And typically, you think of the metal as serving as the catalyst for water oxidation to make that process as easy and efficient as possible. So what would happen if we just take this device as is, shine light on it, immerse it in water, and measure the current associated with water oxidation as a function of time? Well, unfortunately, you get something that looks like this. So the current is really high initially, but it plummets to 0 almost immediately. It's obviously not good. But how this whole project started in our lab really was that we found that if we incorporated a layer of atomic layer deposited TiO2, we could protect the underlying silicon for corrosion. And so that's the degradation mechanism here that's occurring. So without this kind of protection layer, when you try to oxidize water under these very corrosive conditions, you grow this thick SiO2 that kills your device. But you can prevent that from happening if you have this ultra-thin ALD TiO2 layer. So that was a really exciting advancement because it allowed us to use semiconductors like silicon that are very well matched to the solar spectrum. But it actually came with some problems as well. Namely, when you start to think about this metal insulator semiconductor junction and ask yourself, well, we're putting TiO2 into this junction, so what is it? Is it another metal? Is it another insulator? How does it really behave? And it turns out that it's somewhere in between. And some of you might recognize this work from previous graduate students who have come through GCEP and given similar talks. So the two main problems here is that the TiO2 conductivity is really difficult to control. And then also, incorporating TiO2 into this MIS junction also decreases the photovoltage. And the photovoltage is simply a measure of how effective this semiconductor is at taking energy from the sun and converting that into an electrical potential that can drive that chemistry. And so introducing TiO2 is actually not good for that photovoltage. So if we go back to our original structure, after we sort of realized some of the issues with TiO2, we took a step back and said, okay, what are we actually looking for in this kind of metal contact that we're putting on top of the silicon? And so we really came up with 4 parameters that are quite important. First of all, it needs to be highly electrically conductive. That might seem obvious, but we don't want any ohmic losses in our device. It also needs to have what's called a high work function. And this is simply an electronic property of the material that relates to the photovoltage that we can get out. So a higher work function means we get a bigger photovoltage. And then, of course, the same things remain true from the last side. We need it to be corrosion resistant, and we need it to be a good catalyst. So how do we get all of those very different properties into a single material? And our answer to that question has been to look at alloy materials using atomic layer deposition and studied their properties for solar-driven water oxidation. So specifically, I'm looking at alloys of TiO2 and either ruthenium oxide or iridium oxide. And the idea here is that by making an alloy of those two materials, we can combine and preserve really the corrosion resistance associated with the TiO2, but then impart the catalytic activity, conductivity, and high work function of ruthenium and iridium oxide. So those materials are all known to be conductive metal oxides, and they're also good catalysts and have that high work function that we need. And interestingly enough, this is also an analog to the dimensionally stable anode, which is what's used industrially for chlorine evolution. So this was sort of our ultra-thin analog to the DSA, but for water oxidation. Okay, so how do I actually make these alloys? Well, I'm using an all-ALD process, so all I need to do is set a cycle ratio between the number of TiO2 cycles and the number of iridium oxide cycles. And that cycle ratio controls the amount of iridium that I get into the film. And then I simply repeat that cycle ratio for a given number of supercycles to control the film thickness. And so as you can see in this figure, which shows the amount of iridium in the film as a function of the cycle ratio, I can very precisely control the amount of iridium that I want to incorporate into my film. And that's really one of the advantages of doing this by an all-ALD process, is the level of control that we get. Okay, so now I'm going to just sort of walk us through those 4 points that I talked about a couple slides ago and sort of check them off as we go. So the first thing we wanted to look at is the conductivity of these materials. And one way that we assess the conductivity is through a technique called cyclic voltammetry. And all we're doing here is we're applying a potential, and then we're measuring the current associated with electron transfer to and from a molecule in solution. And when we do that, we get these funky curves that are actually called ducts. And really, if you're not familiar with cyclic voltammetry, all you need to take home from this is that the tighter that duct is, the more conductive the material is, the more stretched out that duct is, the more resistive it is. And so what you can see is that there's a very strong dependence on the conductivity of the materials on the amount of iridium that's in them. And it goes as you would expect. So you incorporate more iridium, the material gets more conductive. Less iridium, it starts to get more resistive. But these materials are all more conductive than TiO2 would be on its own. And that's that orange line there that's just a TiO2 film with no iridium in it at all. Okay. So we have good control over the electrical conductivity, and we can tune it to make these materials highly conductive. So the next most important thing to look at is, do these materials generate the high photovoltage that we need out of this MIS junction? And to do that, we use the same measurement, except now what we're doing is we're comparing P plus silicon samples that we measure in the dark to N silicon samples that we measure in the light. And essentially, the difference between the center of those two ducts is representative of the photovoltage. And what we see is two things. The photovoltage is independent of the amount of iridium in the film, which means it doesn't take much iridium to set that high work function that we need. And also, we're getting really high photovoltages, over 600 millivolts. And this is really good for just this simple silicon MIS junction. So this was a very exciting result. Okay, so now onto the third point, studying their catalytic activity. And this is where things got a little bit complicated from my perspective. So I'm just going to zoom out a little bit and actually talk about just ALD iridium oxide, so no TiO2 here at all. We're using the same technique of cyclic voltammetry, except now we're actually looking at water oxidation current. And if you'll just take a look, we do this in base, neutral, and acidic pH. And if you look at the curve in base, which is that first curve on the left, the thermodynamic potential is indicated by that dashed line. It might be kind of hard to see, but it's at about 0.4 volts. And you'll see that we don't start getting significant water oxidation current until over 0.8 volts, which means we have an overpotential of over 400 millivolts. That's also not good, especially because iridium is supposed to be one of the best known catalysts for water oxidation. So this was quite puzzling from our perspective. But what I ultimately realized is that I could improve the catalytic activity by subjecting the iridium oxide to a forming gas anneal. And what that does is reduce the iridium oxide that I grow in my reactor to iridium metal, and then presumably it gets reoxidized during the water oxidation process. And for whatever reason, that material seems to be a better catalyst for water oxidation than what I grow as is. And we do have some hypotheses for why that's the case, and I'm happy to answer questions about that. So we found that this is true for the alloy materials as well. The forming gas anneal is really essential for bringing those overpotentials down into the range of about 350 millivolts. And that's what you would expect for an iridium oxide catalyst. Okay, so the last point is their corrosion resistance. And this was also a challenging thing to work on as well. So what we do to assess corrosion resistance is we measure water oxidation current as a function of time. And what you see for this sample, which is iridium oxide on a 30% alloy, you see that the current starts to decay at around 4 hours. That's also not great, right? We need these things to last days, weeks, months, ultimately years. And so 4 hours is just not going to cut it. But again, turns out the forming gas anneal saves us again. So after we subject the material to the forming gas anneal, we can use this device for water oxidation for upwards of 12 hours. We don't have any evidence of increase in the SiO2 thickness, and we also don't see any evidence of iridium loss before and after testing. And you'll notice there is still a decay in current density. I'm happy to talk about that as well, but we believe that's related more to the catalytic activity than it is to any kind of catastrophic device failure. And so with that, I hope I've convinced you that these alloy materials are promising contacts for N-type silicon photoanodes, especially in regards to maximizing their photovoltage, which is really key. And currently, we're exploring different kinds of annealing conditions to try to optimize the activity and performance of these devices. And we're also looking at fabricating graded structures. And this is really kind of the advantage of atomic layer deposition for this kind of process, because we can control the amount of iridium in the film on a layer-by-layer basis. And what that means is that we can put the iridium exactly where we need it. So we don't need much iridium in order to set the work function. So presumably at the interface between the SiO2 and the alloy, we don't need so much, but we do need more iridium at the surface to be a good catalyst. And ALD allows us to control that all in one process. And so with that, I would like to thank my advisors, Chris Chidsey and Paul McIntyre, for their support, members of the Chidsey Lab and McIntyre Lab, and also GCEP for funding this project in its early stages. That was really instrumental to getting this off the ground, and I'm happy to take any questions.
I could probably guess right you didn't want to talk about TiO2. So you have a gradient of iridium going through the TiO2. Mm-hmm. TiO2, anatase, rutile have different catalytic properties. I'm assuming the gradient of iridium affects the different phases in the TiO2 you're using?
So we've looked at, we've done grazing incidence X-ray diffraction to study what kind of crystalline phases we might have. It looks to be all amorphous. So even after annealing, we see very, very low intensity peaks for anatase TiO2. But in all cases, this material is predominantly amorphous. So we actually have more of a solid solution model for the iridium in the TiO2 as opposed to any kind of distinct crystalline phases. Yeah. No more questions?